Let's see if we can learn something about Flight Recorder today. I'm hoping that's why you're here, because that's what I'm going to talk about. I'm Mikael Vidstedt, work for Oracle. I run the the JVM team at Oracle, and I've been working with JVMs my whole career. A couple of different ones. This is Oracle's not so short way of saying that everything I'm about to say is a lie, so don't take anything for real. Let's imagine that you have a product. It's running a service somewhere, and it's continuously running, and you obviously want to keep it that way. But one day, one night, it's probably Saturday night, right? 2 a.m., middle of the night, there's a problem somewhere. An SLA gets breached, there's a problem in there somewhere. And obviously your job now, in the middle of the night, is to figure out what went wrong. So obviously you start looking through all the data you can find, right? So logs and whatever you have set up in your system. Well, it may well be the case that the data isn't really available, right? You see that the general area where it's crashing or not behaving or whatever it is, that you can see that, but you can't get to the actual root cause of the problem. So what do? Well, at some point you may be tempted to add some more logging or add some specific code that tries to capture more of the data so that you can see what actually went wrong, right? And that's great. The problem is obviously that over time you run it and nothing happens. So you don't get more data. And as a matter of fact, this code you just added probably has some kind of performance overhead or some problem associated with it. So at some point you remove that again. You need to remove it because, well, it's not behaving as like it's adding overhead to your service. And guess what happens? Well, Saturday, 2 a.m. in the morning, you have a problem again, right? So obviously what the flight industry has learned from this is let's capture data continuously, and let's do that in the background. You don't even notice what's happening, right? They call it a flight recorder, and that's effectively what I'm going to talk about. The flight recorder we have worked on is built into the Java runtime itself, but it behaves very much like a flight recorder, an actual real flight recorder. And over the next 40 or so minutes, I'm going to talk a bit about what that is on our level. The agenda looks something like this. I'll talk about the overview of what JDK Flight Recorder actually is. I'll talk about events, because it does turn out that those are central to how JFR works. By the way, I'm going to use JFR, the abbreviation, to mention or to refer to this functionality a lot as well. I'll talk about the fact that JDK Flight Recorder is meant for production. If you leave this room without remembering the fact that this is built for and designed for use in production, I think I've failed. So I'll try to weave that in a few different slides. I'm going to say something quickly about how you can use JFR and obviously some future work, because that's normally how you wrap up a presentation. So what is Flight Recorder? In a nutshell, it is, again, short for JFR is short for JDK Flight Recorder. It is available now in a JDK close to you. I'm saying that because, well, it does depend a bit on exactly which JDK you use, but chances are that the JDK you're using has JFR in it. It's been there since JDK 7. It was there in another JVM before that, and I'll touch on that in a few slides as well. But it is probably in the JDK you're using. It is event-based, so that I'll go more into detail about what I mean about that, but it basically is all around central to the concept of JFR, it's event and capturing events. So again, I'll talk more about that later. It is built into the Java runtime itself, and the nice part about that is that it's sort of an unfair advantage to us. We can piggyback on a lot of the stuff that is happening inside of the JVM and inside of the libraries that make up the JDK, and sort of just store a lot of the information that the JVM already has. So the fact that we have built this into the Java runtime itself makes it very efficient. It has very low overhead. So as a matter of fact, it's designed to have less than 1% overhead in the common cases. That means, again, first reiteration, right? Production, right? This is meant for production. You should be able to run with it turned on all the time and not even notice that it is there in the background. And then if something goes wrong, you already have the data available. The other nice part about having this in the Java runtime is that we can collect events from many different levels. So all the way down from the operating system and the CPU, through the JVM, through the libraries, and also on the application level. You can get events from all these different levels, and you can very easily correlate them. So if something goes wrong on your application level, that an SLA is breached, you can look into all the different sort of details around what else was happening at the same time. And we also have very powerful APIs that you can use both to produce your own events, but also consume the events and sort of make sense of them, analyze them in the other end. So this is in a nutshell, and now I'll go through all of that more in detail. I could start talking more about theory, but I think I'd like to try to just throw a demo at you and see how that works. So I'm going to show you a very simple sort of use case for how you can use JFR. So in this case, what I've done is using, we have all the events already in the Java runtime itself. And what I've done is to build a very, very small agent, a Java agent in this case, a small program that sort of runs in process next to the application that I'm going to run. And it is monitoring the application. So it's taking the event stream, the data stream that is being produced, and it's analyzing that, and it's displaying it in a sort of simplistic way. In this case, it's going to be a text-based representation. Could be something else, of course. I'm also going to use a very old demo, Java 2D. So what I'm doing here is I'm running, how many people know what a Java agent is? Okay, some of you at least. So it's basically just, imagine that you have your main, the normal application main. There's a way to say, here's a jar file, and inside of that I have a class with another sort of main. It's called pre-main. And it's actually running in parallel with your application. So you get the pre-main call first, and you can do stuff in it. It's a sort of handy way just to run something on the side of an application. So basically what I'm saying is run my health report thing here, my special JFR analysis agent, and run that in parallel with the application. So if I fire that up, hopefully we'll see a, well, I think the UI may show up on my laptop perhaps. So here it's coming. So old demo, I'm going to pull that out of the way because it's not really the thing. Guess I need to make that slightly smaller so that it all fits. So basically what you're seeing here is JFR in action. So in the background, in the JVM, in the Java runtime, we're collecting all these events. Some of them are related to GC. It's the sort of the environment we're running in with the amount of memory and all of that. We have allocation rate at the top. There are details around what's going on in the JVM, and then there are two different categories here. The first one is top allocations. So where is the application allocating memory? And the second one is hot methods. Where is execution time actually being spent? This is just sort of a snapshot of what JFR can provide. And the agent, if I show you the code, you'll see that it's very, very tight and streamlined. I'll go more into sort of the details about this later, but just to get a feeling for the kind of information that we're collecting, hopefully this will sort of help put it in perspective. So that was the demo. Oops. Yeah, okay. Some history. I'm not going to go into all the details, but JFR has been around for a long time. As a matter of fact, I worked on another JVM before called JRocket, and we had a problem at some point where we were running into challenges ourselves understanding what was actually going on inside the JVM. So we developed the JVM, but we wanted to know what's going on so that we can improve on it and make it better. And also our support team, they were sitting next to us. They were, you know, I'm going to say from time to time they brought up the fact that we could sure use more insight into what your code actually is doing, right? So that idea sort of was the foundation for what later became Flight Recorder. It has changed its name over the years a bit, but it has been there for 15 years or so. In the let's say the standard JDK, in the hotspot JVM, it's been around since JDK 7. So the very first version was ported over to hotspot in 2012. And we've made a number of improvements on it ever since. So in in JDK 9, we published APIs, made the APIs available for people to use, both for producing and consuming events. And one of the biggest things that happened to JFR was that in 11, which is now a year ago, we open sourced JFR. So now it's available in open source and probably in every JDK more or less out there. This is sort of, you don't need to know all the details about what happened, but that said, it's been around for a long time. So it's very mature technology, so I guess my point, and therefore back to you can use it in production. I'll stop saying that at some point. So let's look at what events actually are, because again, events are very fundamental to how JFR works. So an event is basically this. It is a small blob of data. I'll go more into the storage format of it, but logically it has an event ID, so it's basically some kind of identifier telling which event this is, a unique identifier. There is a timestamp, so when did this happen? There's a duration, so how long did this take? Not all events have a duration. So some can be instant and therefore not have a duration. There's a thread ID, so which thread generated this event, or in which thread was this event, this operation generated. Not all events have a thread ID. Some of them are not tied to a thread specifically, but many are. There's a stack trace ID. So basically, associated with every event, there can be a stack trace, I should say. But in order to keep the footprint of this down, instead of storing the whole stack trace with every event, we are putting the stack traces on the side because they tend to be almost the same. So we're basically storing them separately, and we have an identifier to tell which stack trace to use for this event. And then there's event-specific payload. So depending on which type of event you have various other fields or data points in there as well. Okay, that's still abstract. So let's look at it from a Java perspective. So this is basically what it would look like if you wanted to generate your own event. There are two sources of events, and I'll get to that on a later slide as well, but there are events that are generated from Java code, and that's typically, I think, what if you start picking up and using this and playing around with it, this is what you will see. There are also events that are being generated from inside the VM itself. So that's native C++ or C++ code. So very similarly to the next few slides that I'm going to talk about on the Java level, there's a corresponding functionality on the inside of JVM itself to capture events. So if you want to create your own event, this is what you have to do. It's literally that easy. So you inherit or you extend the class called event, and lo and behold, you have your own event. Cool, right? Okay, so how do we actually make use of that? So let's say that you have some really business critical code, like this is your application. It does something really important, and you want to put an event around it to get some more information. I don't know what it is. Maybe it's processing a HTTP request, or it's calculating some prime or whatever it is. So basically what you do is you add this around it. So you allocate an instance of the event you just created. You start the event. I forgot that I made these things build. So you allocate the event, you start the event, and the begin here is basically taking a timestamp. So it's saying this is when the event started. You do your business logic, and then you call end, which is also just taking a timestamp. So it's basically now, it has the start and the end point, or the duration of the event, right? And then you say commit, and that's actually what takes the event data and puts it into the event stream, stores it off inside of the VM, and we'll see more about how that works. So the first question you might ask is, why would I call end and then commit? Couldn't we just coalesce them, right? And it does turn out that you don't have to call end. If you don't, commit will do the work for you. There is a case where it's useful to make a distinction between the two, and that's when you want to actually have the end timestamp, but there's some kind of computation you want to do before storing the event into the stream. So in some cases, it may make sense to call end explicitly, but if you don't, commit has your back. So typically what you'll see is something like this. But this isn't very useful in itself, right? It's like now you have an event, and the only thing you know is that that event happened. You may want to put some of your own data into the event. So the way you do that is by adding fields to the class, not surprisingly perhaps, and you initialize those fields as part of creating the event. You can do this whenever you want, as long as it's before commit, well, and after the allocation, of course. So for example, if you want, in this case I'm storing constants sort of before the event is even generated, but maybe what you want to do is to take the business logic or whatever, and maybe some value comes out of that, so you want to store that in a field instead. That's totally fine, right? So do it whenever you want, as long as before the commit. So that's basically it. There are some additional things that are helpful to do with your event. So there are a number of annotations that you can make use of. These things help when presenting the data in the other end. They don't modify how things are being produced. But if you want to visualize this later, you may want to provide some useful hints around what the field value actually is, right? I'm not sure I did the best, did my very best naming them here. It's just message and value, right? But maybe you at least want to signify that in some way. And you can also annotate the event itself, the class. There's a name. The default, I'll go through a few more annotations on the next slide, but the default name of an event is actually the full package name and the class name. And in some cases that works out, but in some cases you'll find that your class is sort of in a package called, com.internal.secret something $foo, and it just isn't very nice when you want to present the data in the other end. You may want to have a name that is more easily understandable, let's say. So names the event in a more human-friendly way, so to speak. So that's basically it. Now you've created your event and you've put it into the event stream, and you can consume it later, and we'll see what that can look like. A few additional annotations that you can use are these. So I mentioned name and label. There is a description. So label is supposed to be very, very short. It's like a word or two. Description it's not a full essay, but maybe if you want to add some color to it. So a few sentences, maybe two. So try to keep it short and interesting. There's also other metadata that you can annotate your events with. So as I mentioned, events most of them have durations. And one of the ways we're dealing with the amount of data is by filtering events. So instead of just capturing everything all the time, chances are that some events are only relevant if they are taking long enough, when the duration is long enough. So you can set a threshold on your event. So if you for example, know that HTTP requests that take less than 100 milliseconds, not a problem, don't care. But the ones that take longer, those are typically the ones I want to capture, right? So then you can say threshold, here's the filtering threshold for duration. Similarly, there's an enabled annotation, which basically says, is this event enabled by default? And there's also an annotation for saying if the stack trace should be included or not. So those are some of the configuration options for your events. This list is in no way exhaustive. There are more annotations and more information. The Java docs in the JDK.jfr package is very helpful. So if you want to know more about which annotations exist and when and where to use them, I suggest you go look there. I mentioned that the Java runtime itself generates a lot of events. This likewise is not an exhaustive list, but it does cover some of the key things that we are collecting inside of the JVM and the libraries. There are right now around 140 different events. It is growing. But I showed you a bit earlier in the demo that we are capturing things like the environment, which CPU are you running on, how much memory do you have, that sort of thing. Command line information, version information, both on the Java runtime itself and operating system, things like that. There's I/O, both on the file and network side, GC, JIT compilation, more or less, the expected stuff, I guess, is in there. But again, this is something we're constantly working on expanding on. So in the background, this is sort of how it works. So I mentioned that there are sort of two sources for events. One is generated from Java code. That's what we saw an example of just in the few previous slides here. That's the top cloud thing there. And there's also JVM level events, so things that we feed in from the JVM through the native code, more or less. These both go into buffers, and those buffers are thread local. So that's very powerful because what it means is that there's no cross communication across sockets or CPUs or even threads. They all go into thread local buffers first, and that's very efficient. It's just storing things into a thread local buffer, and that we're very, very good at that, let's say, optimizing that. What then happens is that as the thread local buffers fill up, we store them. We sort of take the buffers and put them into a global list of buffers. This is obviously the uncommon case and also something that can happen sort of in the background, right? So this is being processed by another thread. And once the global buffers fill up, we store things into what we call the repository, which you can think of as sort of a file, a recording file in the background. Obviously, we stored that data to file when the buffers fill up. The other case, which is new with the event streaming functionality that I'll touch on later, is that we now also try to do this on store things into the repository almost every second, or approximately every second. And the reason is that we want to, again, I'll go into this more in detail later, but we want to make sure that the repository can constantly be observed. It's sort of in an observed state and has the most recent data in it. But there's a trade-off between putting the data there all the time and getting data in a timely manner. So basically, what you'll see going forward is roughly once a second, where we're going to store the data into the repository. But again, this basically means, if you take anything away from this slide, it's that the overhead of producing events is, from the application perspective, more or less zero. Okay. So what does a flight recording file look like? So in the end, again, we store things into the repository, and the end data format that we use for this is the flight recording data. And it's a binary representation, and it's trying to be very compact. It is not compressed, which is something we're looking into potentially doing in the future, but it is very compact. And this is something we've improved on over time as well. A lot of the identifiers and the stuff I mentioned goes into an event tends to be, you don't need the full 64 bits or whatever it is. It's like most of them are 0. So var ints happen to be a very efficient representation of that. So we're using that extensively in the flight recorder format. The files are also self-describing. And what that means is that you don't have to know, like obviously there's like a high-level format you need to know about how JFR recordings work, but the events themselves are self-describing. So we capture all the meta information about what an event looks like, which fields it has, how to interpret those fields, what types they have, sort of. All of that is captured in the recording itself. So if you add a new event, for example, you don't have to have the side information about which fields you have. That's all in the recording. So the recording is sort of self-describing, stands on its own feet. I'm not going to go into all that much more detail around what exactly the flight recording file looks like, but hopefully you get a sort of rough understanding of that. I mentioned that events can be filtered. The obvious one is on a type or name basis. So you can say that these events I want to include, these other events I don't want to include. And I also mentioned that you can filter by duration. And we find that the combination is very powerful. Most of the time, as I mentioned, you're probably not interested in the like nanoseconds or even necessarily microsecond events. It's when it's starting to come up in milliseconds or seconds, that's where it gets more interesting. But you can filter on the duration and different durations for different events. I also mentioned that the fact that we are capturing events from many different places can be very powerful. So again, we capture things everywhere from the operating system. So what operating system are you using? The versions of things, the CPU load, that kind of information, through the JVM, so JIT compilation, GC. What else is going on? Class loading in the JVM, locks, synchronization, and all the way through the libraries. And if you, again, do application-specific events, you get all of these events in the same stream. And it can be very powerful to sort of start from the top. So you see that your HTTP request took a while to execute, right? And I'm actually going to show them on this later as well. So in order to figure out what actually happened, you can sort of dive in and go as deep as you want to find what actually led up to that problem, why it did take so long in the end. Right. Okay, I have a whole section dedicated to the fact that you can use and should use this in production. So a lot of this I already sort of covered, but it has extremely low overhead. The concept of having thread local buffers and the JVM piggybacking on the fact that a lot of the GC and JIT data is something that the JVM already collects, and we can just take that data and store it into the event stream, right? That means that this does have very low overhead. We generate events into these thread local buffers, which means that the application won't block. It can continue executing. It's just doing some thread local stores, and that's very fast. And if you still aren't convinced, maybe this will help you. So we have JFR default on for our Oracle Fusion apps. These are the like big, I'm not even sure what kinds of applications we have. We have customer relationship stuff, and it's like, I'm a low-level Java guy, but we have cool applications. They're all running with JFR enabled. And we also see customers who extensively make use of JFR throughout their whole deployments. These are, really huge companies, hundreds of thousands of machines or instances, that sort of thing, right? So I'll try to stop rubbing it in now, right? But this is for production. It's not just for development. But still, Mikael, you keep talking about this performance thing, right? And you keep telling us that it doesn't actually like have overhead, right? But surely that can't be true. If we go back to our example here, I've now sprinkled all this code around my business logic, and surely that will mess things up, right? Well, so to start with, let's have a look at what actually happens here. And this is going to be a journey through how the JVM does optimizations. So I did add a few lines of code, I'll admit that. The begin thing, we'll look into what it does. Commit may be the obvious candidate for like, how can that possibly be efficient? So let's look at what commit looks like. The first thing I'll say is this is not what commit looks like, but it's sort of what commit looks like. It actually is, for various reasons, bytecode generated, not an actual method. But it sort of looks like this. So the first thing it does is ask, is the event enabled? If it isn't, there's an early out to say, don't do anything else. There are other checks. So for example, I mentioned duration. So if the duration isn't big enough, like if this event didn't take long enough, then we'll also early out and say, yeah, event isn't interesting. And there are also other checks that are being performed to see if this event actually should be stored into the event stream. These checks are all relatively cheap, but obviously they're there. And in the end, if the event is actually to be committed, then we call the equivalent of, let's say, actually commit down there. And remember, even that is actually cheap, right? It goes into thread local buffers. But let's have a look at what happens then if this event isn't enabled. Because that's, at least the first thing, right? If we can't get that right, surely performance will not be good. Okay, so going back to our example. This is what the code looks like right now. You have your really important business logic there in the middle, and obviously you want to make sure that that's executing, it doesn't have the rest of the overhead. So the first thing we do inside of the JIT compiler is we use one of our secret weapons, which is inlining. So we start looking at all these method calls, and we look at what they actually execute, and we put that in the method that is calling it. So in the case of begin, I mentioned that the only thing it actually does is take a timestamp. So we inline the timestamp thing. In the next step, it turns out that that is actually a JVM intrinsic. It's something that the JVM knows really well how to get. It's actually a CPU register, the CPU, the read the timestamp counter instruction in the end. So it's very, very cheap. And we know how to optimize that, let's say. So we put that there. Awesome. Commit, likewise, we inline, and I didn't inline all of a commit here, but I did inline sort of the top check, right? So we're saying if this is enabled, do stuff. Well, we can inline that as well. So, and if it turns out that the event actually isn't enabled, we'll get the value false. And the second secret trick we have in the JVM is dead code elimination. We know that that's not going to be executed, so we just remove it. Now we know that this event, we allocate it and we store a value in it. Well, what we can do is use our third secret trick, which is scalarization. We don't have to store things in the actual instance on the heap if nobody's going to be around to read it, right? And this event clearly isn't used anywhere else. It's local to this stack frame. It's local to this thread. So therefore, we don't actually need to store the value on the heap. Great. Now we have a stupid allocation. Let's remove that because nobody will see it. And guess what we'll do then? We'll use our second weapon again, dead code elimination, and business logic, right? And the story is sort of similar for the other checks, right? In the end, basically what this comes down to is, it may look like a lot of code, it may look scary, it may look like it's not performing well, but the JIT compiler is really good at this. And basically what you'll end up with is something that is extremely cheap. 0 if it's not enabled, really cheap if it is. Okay. Some bar charts, because everybody loves bar charts. This is showing JFR disabled, which is 0, as I said. It's enabled, and I will come back to the stack depth part in a bit, but it does have an overhead. So yeah, I'll admit, it's not 0 when it's turned on, but it's very, very small, as you'll see. There are a few other comparisons here as well. It's log4j with off, which still has an overhead. It's log4j with info, which you can see is pretty costly compared to the alternatives. Anybody dare guess what Java util logging info and redirected system out, how big those will be? Well, they didn't fit into this chart, let's say. So changing the scale a bit, you'll see that, yeah, they have ridiculous overhead. Now, it says your mileage may vary at the top. Your mileage will vary. This does depend on what you're logging, where you're logging it, all of that, right? But just to get a feeling for the kind of performance you can expect from JFR, it is very, very close to 0. That's what we designed it for. So less than 1% overhead, that's the goal. We're trying to keep it there. There are ways you can mess that up. So again, if you actually start generating events with long stack traces, that's one of the key sort of things that is costly for us, is taking the stack trace of the running thread. So if you have very, very deep stacks, and you generate these events in some like innermost hot loop, then you will see overhead. But in the typical case, you won't. The default configuration, again, is tuned so that it doesn't have more than 1%. There are other configurations you can run with. So if you start collecting allocation profiles, for example, or again, just capture a lot more data, then yes, there is an overhead. But we get a lot of detailed information using the default profile. Okay, so if you want to use this, how do you get started? I'm going to cover the JDK 11 Plus case here because, well, I like to talk about JDK 11 Plus. There are options for older JDKs as well, but this is what it looks like in 11 Plus. So the option that you're looking for is start flight recording. And there are sub-options to that. So the second example here shows how you can start recording and ask it to store the data to a specific file. Otherwise, it will just record it sort of in the background, and you'll have to go in and get the data out explicitly. So if you start it, as the second line says, then you'll store the data to a file called tempfoo.jfr. And you have your application arguments after that. If you already have a VM up and running, and you didn't specify start flight recording, but you still want to get data out of it, there's a command in your bin directory called jcmd, or jcommand. And it has options to start the recording and to get the data out as a file as well. So that's the jfr.start. You can, by the way, specify to jcmd either a process identifier or the name of the main class. Obviously, that doesn't work if you have many applications running the same main class, but those are options, let's say. And there are also sub-options that you can specify to limit the amount of data you get out and so on and so forth. So I'll show you a quick example of what that looks like. I wish that switching time wasn't a thing. Let me kill that. So this, I'm going to run, much like I showed you, I'm going to still use the Java 2D demo, and I'm going to run it and say, take the default profile, these default events, and store those into a file called /temp/j2d.jfr. I should prove that I should remove this file to make it clear that I haven't cheated. So I'll start this up, and I'm going to run it for a short while to sort of have it collect some information in the background. I like clicking around and seeing what weird stuff is in here. Very psychedelic. Okay, so we've run it for a while. And if we now go and look, we'll see that we have a file. Yay. And there's another handy tool that you can use to look at this. So inside of your bin directory again, so if I go look in my Java home on the bin, I will find a JFR command. This is also new since, I want to say, 11. Could be off by a release or two. This is actually one of the challenges with the release cadence we have right now. We're releasing one release every 6 months, and it's really hard to remember what went into which release. But I think it was 11. Should be close at least. So if I run that, I'll get some handy information about what I can do with it. So it's also saying if you actually want to capture data, here's how you do that. You can use JCMD as well. And it's telling you that if you want to print out and analyze what actually went into the recording, you can do something along these lines. So print the events. This will obviously scroll. These are a number of, like, large-ish number of events now that scroll by. As you can see, they're sort of human readable and nice. There are other ways you can get the data out. So you can, for example, say, I want that exact same information, but as JSON, because JSON is cool nowadays. You'll get it as JSON instead. You can look at summary information. So maybe I should have started with that. So I can say summary. And I'll get information about what version of the JFR file format, whatever, is used here, how many chunks it has. So this is actually back to sort of how data is stored. So inside of that file, we are storing things into chunks because, like, we do want to deliver data continuously in some way. So there are chunks that each, like, stand on their own feet again, right? And inside of this file specifically, we only have one of them. We see when the recording was started, how long it was going for, and the events that went in, right? So this is a histogram sort of the kind of events that came into that recording. Yeah. So those are all cool ways of looking at JFR. Repeated on this slide for simplicity. Oh, you can also say category. So one of the annotations that I think I had on the slide was category. So that's another sort of high-level presentation way of saying this event is logically part of a group of other events. So we have one category called GC, for example. So if you only want to print out GC events, you can say -- categories GC. And you can define your own categories as well. It's not going to go into the details. Okay, so what is JFR useful for? Production, okay. But apart from production, you can also use it for other things. Like the obvious thing is development. So you want to know, while you're developing your application, what methods are actually hot? What is allocating memory? How can I make this run faster or more stable, in a more stable way or whatever? So development is another obvious use case. The one we found interesting was actually testing. So it turns out that as part of implementing JFR, and especially the event streaming stuff I'll touch on in a minute, we found that using JFR to test JFR was actually extremely powerful. We can capture data that we otherwise just wouldn't be able to, and then analyze that whatever operation we expected to do a certain thing actually did the thing in the end as well. So this is true for things like allocation or lock profiling. If you, like the profile suddenly changes, right? You make a change and all of a sudden you have lock contention and everything grinds to a halt. Or maybe not a halt, it just goes more slowly. Maybe it's 10% more slowly, so that it's very hard to see, right? JFR can potentially help you figure things like that out. Okay, so that's sort of in a nutshell what JFR has been for a long time. One of the key use cases we've been missing is continuous monitoring. So for better or worse, the way JFR was implemented was more for, let's say, profiling, spending time like a minute or 3 collecting data from an application, dumping out that data, and then analyzing it. And that's powerful for many use cases, but one of the problems is if you actually want to use it continuously, right? If you have to wait for a full minute and then go through a number of steps, then that's cumbersome. So I'm going to talk a bit about future. Some of the future is almost here already, but I never promise that anything goes into releases. I can only say that the event streaming stuff is in mainline right now and is therefore highly likely to make it into the next release. Do-Care is holding a beaker because that's what we do in the labs. If you watch carefully the beaker, it will now change to a coffee beaker sort of thing. Instead, you wouldn't believe how much time we spent internally working on the color of that coffee, by the way. So as I mentioned, today, as in all the shipped versions of JFR, you basically have to go through the cycle of starting the recording, stopping the recording, and dumping out the file every time you want to look at the data. And that's not exactly ideal. It, again, can work well for your development use case where you're just doing profiling. But if you want to actually look at your running service somewhere, that's not exactly what we want to do, right? So we have worked on something called event streaming. It has a JEP number or a JEP and a JEP number associated with it. JEPs are JDK enhancement proposals. They're sort of a description of what the functionality is and some pointers to more data around what's going on. The goal here was to provide functionality that, again, you can use to continuously monitor what's happening inside of the instance, and also provide the necessary APIs to make that easy. Our goal was to create sort of make it more or less a one-liner to consume data and act on various things. We didn't get it down to a one-liner, but I'll show you on the next few slides that it's at least relatively, I want to say, straightforward. So this is enabling you to do continuous monitoring while the recording is still in progress, right? So we're continuously recording things, and given that we now dump the data out to the repository approximately once every second, you can observe it, you can consume it and act on it approximately every second. So what can consuming look like? So this is sort of the canonical example of consuming events. It is opening the recording stream. So this, I should have included the package here. I think it's jdk.jfr. something. Maybe it's just JDK JFR. We can look at that later. But in either case, we're opening up the recording. We're saying enable one event. In this case, it's JDK Java monitor enter, which is, well, locks, synchronization starts. And do that with a threshold of 10 milliseconds. Actually, I think I bold-faced that as well. Start the JDK, Java Flight Recorder, Java Monitor Enter event with 10 millisecond duration. So any event that takes longer than that will be captured in the stream. And then we're going to say, if one of those events occur, if we see that in the event stream, then do this. So in this case, we're going to say print it out to standard out. And I'm not going to go into the details around, but basically one of the fields in that event is called monitor class, and it's the type we're synchronizing on. And that call there gets that as it's not Java lang class. You're getting a representation, a JFR specific representation of a class, of a type. I'm not going to go into the details, but in either case, it's going to print out the event, believe it or not, the type associated with the event. And then you say start. So start here basically is a synchronous call. It's going to block until the event stream is closed in the other end. There are asynchronous calls as well that you can do, methods for processing this in a separate thread. But it's going to do all of this, and it's going to print it out. If you want to add another event, it's very similar. So in this case, we're saying CPU load, enable that, do that with a duration of 1 second, and print it out when you get it. So I'm going to try a much more complicated demo. Let's see if the demo gods are with me. So I know literally nothing about Spring Boot, but I'm going to use that anyway. So I've implemented a small agent, a monitoring agent. And it's actually, this time it's not going to run in process, it's going to run on the side. So it's going to run on the same machine, my laptop, but it's going to run in a different process on the side. So what I'm going to do is to start up a Spring application. I'll show you the code in a minute. What I'm doing, oh, you can't see that. But basically I'm saying start flight recording, and I start up my Spring Boot thing. So this could be any app, let's say. So I'll fire that up. And meanwhile, in the background, so that's now running. In the background, I have this application going. Oh, you can't see that either. And I'm not sure how to make the font bigger here. Okay, but in either case, I can't really talk to this anyway because it's Spring Boot and I don't know Spring Boot. There is a small application here. Basically what it does is it sets up a few REST endpoints, I think they're called. And very specifically, they look sort of like this. So there's a /hello endpoint. You really can't see this. Presentation mode, excellent. Where's presentation mode? Presentation mode. Sweet, good. There. Thank you. Not that one. Not that one. There. Good. Hello. So if you go to this web service /hello, you'll simply produce something that says hello. There are a few other ones here, and that's what we'll be demoing. So hello 1 does almost the same thing. It's just it does something CPU intensive. So imagine that I have some weird request here and it's consuming CPU. I'll obviously want to know what's going on, right? So keep that in mind. Hello 1 is CPU intensive. Hello 2 is GC intensive, so it does something weird with allocation or something, right? Should maybe be clear from the name. And Hello 3 will be using lock contention. So these are 3 sort of use cases or 3 weird things that can happen. Obviously this is a fake application, but in theory this could be your production code or whatever, right? So I have a small agent on the side, and it basically does what I just showed you on the slide. So it's opening up the recording stream. It doesn't do that in the same process. Instead, what it does is ask around for JVMs that are running on the same machine, and it's opening up the recording directly from the repository, so like from the outside. So basically what is happening now is that I have the Spring Boot instance that is producing data into the repository, into the file stream, and I have this other process that is now observing that exact data. And what we made sure with event streaming is that the data is always consumable, it's always consistent, right? So you can always get to it and observe it on the side. So what that looks like is something like this. So by the way, if you're paying attention, you'll see that I'm running Java on a Java file. I'm not compiling it first. This is new functionality in some release that is relatively recent that I've forgotten exactly which one it is. But if you have a single main class with a main method in it, you don't need to run Java C. You can just run it directly with Java. Cool, huh? So as I mentioned, what this is doing now is looking around for processes, JVM processes on the same machine, and it's now found one. It's the Spring Boot thing, not surprisingly. And what I'll do now is I'll first run hello, just to see or show you what's happening. So the monitoring agent, we should make that slightly bigger, did notice that the hello endpoint was being accessed. Hello 1, if you remember, is a CPU intensive one, so now it's going to run the CPU intensive thing. And hopefully, as you can see, it took slightly longer to access, and this looks like a crash, but it isn't. It's actually printing out that one event took a long time, the CPU event here. So what I've done is I've opened the recording stream, I've added a subscription to the CPU load event, or JDK execution sample event, and I've said if it takes longer than this, print it out for me. And basically that's what we're seeing here. It found that something was taking time, and you can see that in the stack trace here. Maybe I'll make that slightly bigger as well. You can see that it's the CPU intensive method, much like we'd expect. Hello 2 is the GC intensive one. And I'm not sure why it started accessing the error thing there, but in either case, we see that there's a GC pause. And the reason being that we have a GC intensive thing running. And then finally, we have the lock contention case, which is going to tell you that there's a wait here in the lock contention method. And you can also see that the class we're synchronizing on is object. So these are examples of sort of very simple monitoring. I'll show you just very, very quickly what the monitoring agent actually looks like. Just to give you a sort of quick view of that. So it should be relatively similar to what you'd expect. So here's an event stream. We're opening it up and we're saying on the HTTP request event, if the request takes a long time, then get more information and show that. That's sort of in a nutshell what happens. Cool. So that's event streaming. I want to say that with event streaming, we are effectively, in my mind, we have the first real version of JFR. It's always been powerful, but the fact that we now have event streaming in there is providing that use case that we've been missing in my mind. So obviously there's more stuff that we can work on, but that's sort of one of the key things that we needed to do to have the full story in place. Some of the other things we're working on is making it possible to access the events over JMX. We want to, as I mentioned earlier, keep adding events. There are other things, especially on the JDK libraries level, that we want to feed into the same stream. So which crypto algorithms are being used, certificate expiration dates, that sort of thing, high-level stuff. There's a project called Loom, which is looking at providing fibers and continuations. Not going to go into the details, but basically it turns around a bit the concept of what a thread is. And since threads are so key to how JFR works, that's something that we need to look at how we can support with JFR as well. The command line is something that it's always hard with usability in command lines, but I think we can do some tuning to make that slightly easier to use. There are a couple of other things that we're looking into. Event throttling. So instead of just filtering on name and duration, maybe you want to record sample every nth event of a certain type, that sort of thing. And deep tracing in the sense of maybe for a short duration, you actually want to capture everything just to get a very, very detailed view of what's going on. So this does put some stress on the code that is capturing events and making that efficient and all of that. There are a lot of integration opportunities here. So JFR, the stuff I've showed you is obviously very sort of low level and provides the primitives for getting the data out. The next step that we'd like to see is more of the big libraries, frameworks, and IDEs picking up and making use of this, visualizing it, helping it, like providing it to the user in a well-shaped form, so to speak. So we're providing the primitives for doing this. As I showed, hopefully, like getting specific data out isn't that hard. It's like a few lines of code. But I think what we're hoping to see is that this will be picked up by a lot of the vendors out there. And if you want to try this out, and please do try it out, we are relying on your help to figure out what to do next and make sure that everything works as you'd expect. So please do try it out. We have obviously shipped releases with JFR in it. We are also providing early access binaries of the next version of Java. So in this case, that's JDK 14. You can pick them up, you can try them out, and let us know what you think. There's an email list here, a mailing list that you can send feedback to. And just as a summary, this is actually the same slide as the in a nutshell thing that I showed at the very start. So Flight Recorder is JFR, JDK Flight Recorder. It's there right now already. Event streaming is not in a released version yet, but it's coming soon. It's event-based, built into the Java runtime with all the unfair advantages that come with it. It has very, very low overhead, and it's production use, right? Remember that, production. You can correlate events from many different levels, and we have APIs both for producing and consuming the events that we like to think are very simple to work with. So with that, I thank you, and questions? Do we have time for questions? We do not have time for questions. I'll be around, so